Okay, it says there. We're live.
Yeah, we are live now.
Oh.
You can start.
All right, good morning, good afternoon, good evening, everyone, depending on where you are joining us today. Welcome to day 2 of the Mexican NLP Summer School. I'm super excited to be introducing today's speaker. Before that, just one logistic about this. Please remember that you can type your questions in the Q&A chat if you're joining in Zoom. If you're in the Slack channel, you can type them on the general session. And if you're on YouTube, you type them on YouTube and we'll collect them and we'll make sure that we process and get to as many questions as time allows. And for people on Zoom, you have the option of letting us know if you want to ask your question, and you can unmute, and then you will be able to unmute yourself. Okay. All right. So our first speaker this morning is Professor Rada Mihalcha. She's professor in the Computer Science and Engineering department at the University of Michigan. She's also director of the Michigan Artificial Intelligence Lab. Her research interest is in computational linguistics, lexical semantics, and computational social sciences, among other things. Rada is one of the very, very active researchers in our community as well. She has been organizing program co-chair for several of our conferences. She's an ACM fellow, a AAAI fellow, and then currently serves as the president of the ACL, the Association of Computational Linguistics. She has been awarded multiple recognitions. Among them, she is the recipient of the Sarah Goddard Power Award in 2019 for her contributions in diversity in science. So in addition to being a stellar NLP researcher, Rada Mihalcha spends a lot of time in pushing efforts for increasing diversity in science. And she was awarded the Presidential Early Career Award for Scientists and Engineers by President Obama in 2009. So with that, I'll welcome Professor Rada Mihalcha. She's going to talk today about word embeddings. So Rada, take it away.
Thank you very much for the introduction, and it's really wonderful to see this summer school happening. I think it's very important to have such events, and it's wonderful to see all the participation. And I know it comes with a lot of effort to organize such an event, so kudos to the organizers. But I'm sure many will come away with enriched by this event, myself included. So thank you very much for the opportunity to share with you some of the research we've been doing in NLP, and also some thoughts that I have primarily regarding word embeddings. So let me share my screen. All right. So I'll be trying to keep an eye on chat in case there are questions. And I know there is also simultaneous translation. So if at any point I'm going too fast, please do feel free to ping me so I slow down. And as Tamar said, what I'm going to talk about today is word embeddings. And of course, word embeddings don't really need much of an introduction. We are all familiar with this kind of word representations, which are a fundamental block in natural language processing. And really, they have been around for a very long time. With this kind of terminology, maybe just for about 10 years, but really word embeddings are just word representations that we've been using almost since always, since we started talking about natural language processing. Also, the field of information retrieval has been using word representations in different forms, not necessarily what we currently use today, but we've been having this kind of representations for a long time. And the core idea really is to represent words as vectors, which is really a simple idea in a way, but it's very powerful because it gives us the ability to really do math with words. So if we take words as discrete representations, say if we take Mexican as a word and summer as another word, it's really hard to do any computation. However, if we translate them into vectors with numbers, then all of a sudden it's a different ground, and we can do a lot there. So just to make sure that everyone is on the same page, I assume this is very familiar to many of you, but I'll repeat just like I said, to make sure we are talking about the same thing. So we've been seeing word representation for a while. When information retrieval started as a field, it was primarily seen as a vector of which documents in a collection contain a particular word. Nowadays, we primarily talk about these vectors that are a byproduct of training neural networks. And this is an example that many of you have likely seen, showing how we can compute with such words. So for instance, if we have a representation for the word king, and another for man, for woman, for queen, then if we subtract man from king and we add woman, then we get a representation that is fairly similar or close to the representation for queen. And here is one way of doing that. This is coming from this paper by Tomas Mikolov in 2013, where there was this neural network that was proposed, either using continuous bag of words or skipgrams, where the core idea is that we can use any running text as training data, and we try to predict either a target word, a given word from the context. So that's the continuous bag of words idea, where we have some words in context and we try to predict a target word. Or conversely, we have a word and we try to predict the words in the neighborhoods to the left and right. So basically that gives a lot of training data. Any running text will turn into a training, several training instances. And if we train a neural network on top of this data, then we end up with representations for words, with vectors, with dimensions that we can set as a hyperparameter. 300 happens to be a commonly used dimension for these vectors. It can be other dimensions as well. So here is what we are currently using in a lot of applications. It turns out there are really lots and lots of publications, which are really research ideas, research applications that use these. And here is what we see if we look at Google Scholar. So I had the curiosity to search for word embeddings on Google Scholar, and I haven't even tried to go out of my way to search for paraphrases. So it's really literally word embeddings and nothing else. And that's what we get in terms of publications. And again, this refers only starting about 10 years ago, because as a term, word embeddings was introduced at that time, but word representation, as I said, had been around for much longer. So we can see how it's been really skyrocketing in terms of research that makes use of word embeddings. And at this point, so the last column that you see corresponds to 2020. So it's last year, there were about 25,000 publications indexed on Google Scholar that use word embeddings a way or another. So what are these research publications? Well, I don't usually like word clouds. I think they are kind of superficial, but here is a word cloud for you. It's just reflecting the kind of words that are being used in titles of papers that make use of word embeddings. And we see what we'd expect to see, which is semantics and language and analysis. But then we also see tasks such as classification. We see sentiment analysis, similarity, cross-lingual analysis, multilingual classification, biomedical, and so forth. Okay, so core message here is that really there is a lot that is happening in this space. Now, here is one way to look at this, and an analogy that I've been making. I was thinking about word embeddings in particular, but I think this same argument would apply to NLP more broadly, and even AI as a field. That we were at this point several years ago. So there were these disparate pockets of research that were addressing different problems, which were all maybe working reasonably well by themselves, but it also was not necessarily making a whole. So that's sort of the state of the field, and primarily looking at word representation, I'll say maybe 15 years ago. And then we made progress, and we eventually ended up with putting all these pieces together and having something that looks like a more of a puzzle that's now put together. And we got from there to making even more progress. And here is where I think we are now, to something that looks like a solved problem in terms of what kind of applications we enable with word embeddings. We have made a lot of progress since the one particular embedding that I shared. So now we have contextual embeddings. You probably heard, maybe even use BERT embeddings, which are contextualized, and use those in various tasks in language models and so forth. So looking at it, you'll say, well, it's almost a solved problem. We are getting state-of-the-art results on a number of applications. Now, the other way to look at this, it's also to see that this is really a facet of a bigger problem, right? So if we only look at the wide facet, which primarily focuses on accuracy, on all these state-of-the-art results that we see out there, we will say, well, we are almost done. We can now move on and do something else. But another way to look at it, which I think is really the more realistic way to look at it, is to acknowledge that this is really just one facet of a bigger problem that we are here to solve. And so there are all these aspects primarily focusing for this presentation on word embeddings. But again, I think the same argument applies to NLP as a field, or even AI as a field. There are all these other facets that will really require our attention. And I want to convince you here, with our researchers who are now sort of going to make a difference and really the future of our field, to consider taking some of these other aspects in your research and try to solve some of these other facets. So I'll go through what I believe are the other facets one by one and just illustrate what are some of the issues that we see. So one facet, which is very relevant for word embeddings, is interpretability. So I want you to spend a little bit of time and just think of this word and what this word brings to mind. And some of you may think of just purely definitional interpretation, cat is an animal. Some of you may think of your cat at home or your parents' cat or a cat you saw on the street. But there are certain analogies and connotations that this particular concept brings to mind. Now here is another one. Again, if you spend just a little bit of time to think about this, there will be certain things that will come to mind. Again, it can come from a dictionary. It can come from a movie that you saw where there was a fire and so on. Now, here is another one. So I want you to look at this and try to think, what does this bring to mind? And chances are it won't really bring to mind anything other than, well, some numbers. And okay, we have some connotations for numbers, but that's about it. And the reality is that this is really what word embeddings are. So when seen from the outside, we see a series of numbers, and we are supposed to interpret that, and we cannot really, and that's understandable because they are pretty opaque. They might make sense to a neural network. They might make sense in a downstream application in the sense of the systems themselves being able to extract some meaningful signal from them, but they are very hard to interpret. And the reason this is relevant is first as a vector in themselves, right? So when we look in the exercise we've just done, if you look at as a vector, can you even tell what kind of word is that it's close to what, and so forth. So for the vectors themselves, it also is important for interpreting the relations between vectors. So I showed you earlier the distance between vectors and how that would have some kind of meaning. So if we take king and queen, maybe they are related to one another. So say, okay, we can come up with some kind of a distance that is similar between king and queen and man and woman. But how about if we take, say, vector for king and castle? So these are not necessarily similar concepts, but they are related concepts. And what would be the meaning of a distance between these two vectors? Even more complicated, although not necessarily complicated for humans, but will be in this vector space. How about if we take north and south? So they are related concepts, but they are in opposition of one another. So what kind of distance do we want to have between them? And of course, if we take a look at good old WordNet and all the semantic relations that we have between words, so we see hypernyms, synonyms, but we also see opposition, derivational terms, holonyms and meronyms. So there is a very complex space of semantic relations, which currently is really not clear on how we can encode with these word embeddings and how we can interpret. So even if they encode them, how can we interpret them or uncover them in a way that's meaningful either to a user or to possibly some application that make use of these relations. So that's it when we consider vectors by themselves or relations between vectors by themselves. There is also the setting that I mentioned of word embeddings being used in downstream applications. So we often use them as features in applications such as sentiment analysis or general text classification and other tasks. And say if we figure out when we do this kind of application, say we consider sentiment analysis, we have text that we want to classify with respect to whether they are positive or negative. And we figure out that, say, from the features that we put in, which include some word embeddings, there is the element number 2 and 7 in a word embedding that really makes a difference in some kind of feature ablation. What do we do with that information? We don't even know what those mean. So interpreting the results, doing feature ablation when some of the features are word embeddings is not necessarily clear what it means. And there is also this other issue which I'll address later, and you'll probably run into if you try to use word embeddings. For the particular word embeddings that we use now, which are primarily based on neural networks, it really does make a difference on which space they are trained. So if you train a neural network on certain data, you get certain word embeddings, the vectors have meaning within that space. I cannot really take a vector train on some data with one neural network architecture and put it side by side with another vector coming from another architecture on other data. They really won't have the same meaning. So I cannot put them together. This wasn't necessarily a problem with the previous word representations we use, like in the vector space model or distributional semantics, where we could literally read the dimensions in the vectors. But it is currently now with this more opaque representation. So that's something else to consider when it comes to interpretability. So this, I believe, it's one major aspect. There is more work happening now, interpretability being one, and seeing to what extent we can figure out where is the attention being paid. So we've been seeing attention models. We've seen ways to try to interpret the neurons inside the neural network and which are the ones that are activated or not. But I really think there is a long way to go, both in this direction of pure interpretability, also explainability is another direction that's being considered, not necessarily only for word embeddings, but in general in this kind of applications that use more opaque representations. So another facet that I want to talk about, aside for interpretability, there is also this question of generalizability. So if I create some word representations, can I rely on them for different applications or using them for different tasks? And it turns out that's generally not the case. So here is a table of results from a paper from 2019 by Zheng and colleague that looked at the word embeddings that I showed at the beginning. So created with Word2Vec using a very large corpus of language in the open domain, so from Google News, and trying to use them to measure similarity of concepts in the medical domain. And that's what we see on the first row. So we see these embeddings from Word2Vec trained on Google News, and we see how they perform pretty poorly. So Pearson and Spearman are metrics that are traditionally used to measure how well word similarity would work. Others metrics as other tasks as well, but particularly focusing now on word similarity. So we take two words, we see how similar they are according to some human judges, and then we have a way to do that automatically by really measuring the distance between word embeddings, and we see how well the automatic metric does as when compared to the gold standard. And what we see here is that this taking the generic word embeddings just doesn't work. And part of the reason is that it's a different domain. So this is the medical domain, it's not general domain. And so what they found, for instance, that if they train this similar model, so it's still Word2Vec, but trained on PubMed data, so this is data from the medical domain, they got a significant improvement. So the same metrics, Pearson and Spearman, go all the way to 0.6, which is quite a bit larger than what they started with. So what this really tells us is that the sort of off-the-shelf word representations are not really generalizable to other domains. The same findings come also from this other work from Aharoni and Goldberg. This is from last year's ACL, where they looked at machine translation evaluation across domains. So training a system on one domain and testing on another. So we see here how if we train, say, on medical domain and test on medical domain, what kind of performance we get versus, say, training on medical domain and testing on law or Quran or IT or subtitles. And by and large, with some exception, we see that the diagonal is the one that sort of steals the show in the sense of getting the best performance, which really points again to the fragility of these representations. As soon as they sort of get out of their own domain, then they're just not working anymore. So this is something that's important to consider and even think carefully of what does generalizability means, what would be the ideal behavior for this dimension. What does in domain really mean? We've been using this very often. I've been using in domain, out of domain very frequently, but it's not always clear what that means. Does it mean that we stay within the same topic or maybe the same style? Is it keeping the same level of formality? So trying to have a better handle on that in the first place, and then also figuring out how we can better transfer embeddings from one domain to another so that we have this enhanced generalizability. Because the current state of affairs really is that we have these representations that work very well on the domain that they were trained on and completely break when we take them sort of out of their original space. All right, so on to another facet. This is fairness. And it's something that you may have seen recent work on, talking about the kind of bias that's encoded in word representations. And this is, I find one illustrative example from a paper that appeared in 2016 from Volukbashi and colleagues. The title is very representative for what the main argument is. Man is to computer programmer as woman is to homemaker. So really talking about the relations between word vectors and how man has the same relation to computer programmer as woman would have to homemaker. And what we see in this figure that's drawn from the paper is how we have words that have gender encoded in them. So that we see on the bottom of the figure. So for instance, if we talk about fiance or girlfriend or dad or boy or son, these are words that have gender in them. So those would be sort of gender words that we can also use as a starting point to measure what kind of gender is associated with other words that do not have gender sort of hard-coded in the words. So with these kind of words as a starting point, we can actually create this kind of diagram that we see here that will tell us what words are more on the he side or what words are more on the she side, really just measuring with representation like the one I showed at the beginning and seeing the distance. So we say, okay, this is what male or female means in this space by using words that have the gender in them. And then we can see how that propagates to others. And what we find is that according to these representations, there are words such as brilliant or genius, which sit on the he side. So they are closer to words that represent male, and that's really reflecting a bias. So that's in an open problem. Since then, there has been quite a bit of work, either uncovering other kind of biases, for instance, with respect to ethnic groups, or proposing ways to debias embeddings. And to me, I think that's still a very open problem that requires careful thought and a lot more work to get to a point where we have representations that are not encoding, in a way, our societal biases. One problem that I found interesting is also figuring out what words even would need debiasing. And there are certain words, for instance, I think here, dress, it's a word that's more on the she side. And I think that also calls for models that are created for certain groups. So in certain cultures, dress, it might be a more strongly associated with female concepts, and that would be fine. So maybe that word does not need debiasing. But in other cultures, it will need debiasing. So dress would be a concept that should be neutral because it's associated with both male and female concepts. So in general, I think when we talk about fair embeddings, we'll want representations that are unbiased, also that are trustworthy, and importantly, privacy preserving. That's a concept that's now starting to surface more and more on how certain representations may in fact invade the privacy of the people who generated the data. And one example that I like is from research from Emily Maurer-Provost and her team, where they showed how representations that were creating to predict emotions. So really the downstream task was emotion prediction, but they're also revealing gender, which was not supposed to be encoded in those representations. So thinking more carefully about what is really in these embeddings and what we want to have revealed. So privacy preserving, I think it's also an important concept. So here is another facet, which is that of robustness. And the question that is being asked here is to what extent these word representation are stable across embedding spaces. So I mentioned that briefly, that when we train word embeddings, we usually do them on a certain data set with a certain neural net architecture, possibly using a certain seed. And it turns out that they are not really easily generalizable across other settings. And it turns out they are not stable across other settings. So if we consider different algorithms, different domains for the data, or like I said, even different training seeds, we'll get different degrees of stability. And the way we define stability, so this is work that we've done in my group, but I know there are also other groups that have considered and analyzed this concept, is looking at the overlap between nearest neighbors. So if we take, say in this example, a word like international, and we have, say, one round of training that will give us some vectors. And so we have a vector for international, we'll have a vector for also words such as national and Philadelphia and road and many other words. And then we look at which are the words that are closest to international. And eventually what we'll see is that for a certain setting, we get the word that we see here as the closest 10 nearest neighbors. Now, if we change the space, so either we train on a different data set or we change some of the hyperparameters in the neural network, we may get a different set of nearest neighbors. So for the same word, international, we may get words such as metropolitan, national, state, society, and so forth. So the way that stability is defined is looking at what is in common between the nearest neighbors for one word across two embedding spaces. So in this case, we see that there are 4 words in common. So we'll say that there is a stability of 40%. So it's 4 out of 10 would be 40%. So the question is, what is that affects stability? And so we look, for instance, at the stability of words in Pen-tree Bank, which is a corpus that we have been using when working on English on a number of different tasks. And we see how they distribute in terms of relation between stability and the frequency of the word. And there seems to be some kind of relation with frequency, but it's not very clear. So what we thought is that probably there are other factors at play that would in fact affect how stable these word embeddings are. So what we considered are several data sets. So we have data drawn from New York Times for different domains, also data drawn from Europower, and also consider different algorithms. So we have word2vec as an algorithm, which is the one that I mentioned earlier, particularly the skipgram model, also GLAV and PPMI. And we want to see to what extent these different settings play a role in how stable word embedding is. So basically what we've done, we train a lot of models. And for each model that we created, we measure the stability of the words. So as feature, we have a meta-learning problem where the features are some of the settings that we use in the training. So the word itself, so what word is that we are measuring, what algorithm we are using to produce the word embedding, and what kind of data. And we fit a regression model. And with that, then try to figure out what is that makes a difference. So we basically use the weights of the model to learn about what makes a difference in creating representation that are stable. So from this experiment, there are a number of lessons that we learned. First, which was somehow surprising, is that frequency is not a major factor in stability. So we see what was the R-square score for this meta-learning model when we use frequency versus without using frequency. So it turns out that it doesn't necessarily play a role. And by this really means that it's probably redundant with other factors. So when we train the model using only the frequency of a word and try to predict stability, we get an R-square score, which is not 0, but it's fairly low. So that was one, I would say, surprising finding of the relation between word representations and their stability. Another, which I think it's a very interesting research direction to pursue, is curriculum learning is important. So the order in which training instances are provided to the neural network can make a difference. So showing a particular example, training example at the beginning of the learning versus showing it at the end, it can make a difference. And that's what we found, that it's important And this is what we see here, depending on what is the position in the training data of the training instances, we see that there is a relation that with stability. We also found, which is correlating with what I noticed earlier, that there is more stability within domains than across domains. So it's that factor of generalizability that we observed earlier. So we see the diagonal, which is really comparing word embeddings from the same domain. So we have here US as a news articles data set compared against US versus say taking US comparing against business or arts. So we see that the highest stability we have it when we stay within a domain. And another thing that we learn is that part of speech is a big factor in stability. So there are certain part of speeches that are more stable than others. Numerals are more stable than say particles or conjunctions. And also we learn things that have to do with algorithms. So we found, for instance, that word2vec is not very stable compared to say glove, which is significantly more stable. And in fact, this research that we've done has been very informative for other research that we've been doing, primarily at natural language processing and computational social science. We now, if we use algorithms that are non-contextualized, then we prefer glove versus word2vec just because we found that is more stable. So findings that we would have are likely to be more robust. Of course, one question that can be asked is, what about languages other than English? And that's work that we've done recently. We found that there is quite a bit of variation across stabilities for different languages. And this is really just a sneak peek into this research that's coming out now, looking at stability for different languages. And we found, for instance, there are certain languages like Lithuanian that have much lower stability than others, such as Vietnamese. And also what we've been doing here is analyzing the different factors that play a role. So using the WALS list of linguistic attributes that are associated, so different linguistic phenomena for different languages. We are using the same idea of trying to learn what are the factors that make a difference. So for instance, if a language is gendered, like Spanish, versus not being gendered, like English, does that make a difference in the stability of words and so forth? So now moving on to one and final aspect that I think it's relevant and should be considered, which is the environmental and financial cost that comes with creating these word representations. And these are two tables that I copied from a paper by Mashtubal and colleagues from ACL 2019, which looks at the carbon footprint for different algorithms that we use, different neural networks, different applications, and also comparing that with the carbon footprint of other activities that we would do. So what we see, for instance, if we consider air travel for one person between New York and San Francisco, so this will be just as a comparison point, we see it's close to 2,000 carbon as a footprint. So that gives us one point of comparison. So or another point of comparison across human life on average for 1 year, it's 11,000 as a carbon footprint. And now we can look at some models, right? So we see, for instance, BERT, which I mentioned as a contextualized word embedding. And we can see like really the base form going to the carbon footprint column on how training this model really takes the same, that has the same environmental impact almost the same as one person traveling between New York and San Francisco. And we also see some that are even really very, very large. So we see other models here. Some cannot be measured, but we see both carbon footprint and also cloud compute cost, some of which gets to millions. So this, to me, I think it's something that we definitely have to consider. I also think it's the danger of getting into monopoly where only those very large labs that can afford this kind of compute cost can actually build this kind of models. And of course, there is the environmental effect, like really asking the question, are we better at the end if we have these models in place versus how much impact it had on our environment? This is another chart which I found quite telling. This is from the paper from last year talking about GPT-3 and showing here total compute used during training for different models. And we see this is really the number of hyperparameters or parameters that are being used in the model. So we see BERT is the green columns, then T5, different flavors of that will have the purple columns, and then GPT-3. And we see there is a huge number of parameters and also total compute that's necessary for that. One thing that I found particularly interesting and also somehow disturbing that was reported, and I appreciate the authors for reporting that, is the fact that apparently there was a bug that was found when training the GPT-3 model, but they could not afford to fix that bug. So they had to work around it because the cost to fix the bug and rerun would have been too large. So it also comes to how we develop these models if we get into this kind of compute that we cannot afford to rerun it. And so that's something else that I think we should consider. And I'm excited to see more work coming out and looking at green NLP. I know there will be more coming up in terms of conversations that we as a community can have on what matters and where we should say that it's too much. So compute is too much, maybe environmental impact is too much, and what's the trade-off between accuracy and these other factors. So this is another chart that I found from another recent paper from Schwartz and colleagues on green AI, and just looking at the number of papers and what they talk about. Do they talk about accuracy? Do they talk about efficiency, or both? Or do they talk about other factors? And we see that there is this tendency, which we know, to primarily report accuracy. I think there is also an encouraging trend to talk about other things being efficiency, for instance, or other factors that I mentioned today. So with that, I'll go back to my original analogy. I think that's where we really are, where we have one facet sort of solved. So we have all these systems that do so well, generate language that's comparable to human language and human performance, all these classification systems that do really well. But the other facets really are not where they should be. One, I think, potentially rich direction to consider is to bring back the secret NLP weapons. I really think we seem to suffer from some kind of general amnesia. We forgot everything that was done in NLP prior to the last 5-10 years. And there is a lot that was done and is out there. For instance, lexical resources. They are very rich. There is a lot of work that went into them. So trying to consider some combination between these neural approaches and symbolic approaches, I think it's a rich path to go to. I know there has been presentation here on deep learning and structured data. So thinking of taggers and segmenters and parsers and the kind of information we can derive from them and how to make use of that information. Lexical networks, for instance, are really very rich representations as well. And there is a lot more that, other than these neural network representations that can, through combination, like I said, I don't think we should even consider giving up on neural networks. I think that's really, they brought a lot of advances, but we also should consider some kind of combinations between neural and symbolic approaches. And generally, my argument is that we should bring back language. So really remember that sort of that's what we are here for. That's how I feel for myself. I really enjoy thinking about language and all the language phenomena. It's not primarily an engineer problem. Not that there is anything wrong with engineering, but really remembering what is the data that we are working on. It's language. And there is a lot of richness in language, both in terms of using that richness to build better models, and also in terms of what these kind of models can give back to language, like having an understanding of how language evolves, how we use language, what are different phenomena in different languages, and so forth. So what I think will be happening is that we'll eventually move from this state to something like this, where we make progress on some other facets. And with that, we may lose something in accuracy. And I really think that's fine. I don't know how many of you know how to solve the Rubik Cube. I don't, but I've been witnessing my daughter on how she does it. And that's what usually happens. So you get the face ready, and then as you try to get the others ready, you will mess up that first phase, and that's fine. So it's really just natural in the process. And eventually we will get to this state where we'll have the kind of accuracy that we hope, which is really the emphasis that our community has these days, but also have systems that are interpretable, generalizable, fair, robust, and also aware of environmental and financial impact. So with that, I want to thank my research group. There are a lot of insights that came from conversations with them, including for this very presentation, and of course, some of the research that I mentioned. And I think there is some time for questions, and I'll be happy to take questions.
Thank you so much for that. That was wonderful. We do have several questions. So let me see. I want to start with the Vajyoti Majum question. Why do you think the order of training data given to an algorithm matters?
So I think it has to do with what is the state of the learning at that point in time. So it's one thing if an algorithm, if a representation for a word is really at the beginning. So we know, for instance, when we train networks at the beginning, the representations aren't really very meaningful. And as we train more and more, so as we go through multiple training iterations, they will get more meaningful and more robust. So at the beginning, when there isn't really much that has been learned, it's one thing, as opposed to seeing an example when you already know things. The analogy that I would make is with a child, as they learn their sort of first or second word or some of the first words, versus learning a word when you already have a rich vocabulary. So I think it's that intuition that at which point in time you get to see an example, a training example, and what you already know by then can make a difference. We've done a little bit of work in my lab, and I know other labs have done more work on curriculum learning. I think it can be a very rich path of exploration.
Sounds good. So Jonathan Rojas Simon is asking, in your experience, what has been the biggest challenge of dealing with word embeddings in NLP tasks?
Well, I would say all the things that I mentioned. I really focus on challenges that we have. I think the fact that they are not generalizable. So we have these pre-trained embeddings that we can use off the shelf, but they only work up to some extent. And so then having to think of how to fine-tune them or how to get them to a point where they are actually meaningful, I think it's a challenge. And also what we've been running a lot in my lab is the fact that they are not transferable across spaces. So if we say, even thinking of, say, okay, we want to do some cross-lingual English-Spanish information retrieval or something else that would rely on word representations. We all have really to think of how to do that in a way that makes the word embeddings explicit, because they will not be transferable unless we train everything in just one shot or use other tricks to get everything in the same space. But originally they will not be. So a word embedding really has meaning just within the space that it was trained. And to me, at least based on the kind of research that we've been doing in my lab, that's one of the biggest challenges.
Okay, so we have a question from Manuel Montes. He's asking about the biases, and he's wondering what is more interesting, relevant, approachable, if analyzing the biases of different cultures groups through these embeddings, or to try to mitigate these biases in resulting vectors.
I think both. I'd rather not venture to say what's more important. I think both of them are important, and both of them are really big problems. In a way, I would say it's really what speaks more to a researcher. So one is really about understanding what the problem is, and the other is about addressing the problem. I don't think we can call it solved when just one of these is done. So if we understand what's the bias in different cultures and we don't address it, it's just half solved. If we solve it in one language or one culture and we don't know anything about the others, again, only partly solved. And like I said, because both are really big problems, I think it's really what speaks to one researcher or group of researchers as being more interesting. But to me, both will have to be solved, because there are differences. I mean, we know that just from society, there are differences in biases between different cultures, and I wouldn't be surprised if they are reflected in data and word embeddings for different languages. And also solving them is very critical.
Yeah, I agree with that. So Patrick Haller is asking about the studies on stability. When comparing stability of embeddings across different languages, are you using the same corpus size?
So that's a very good question. And yes, we've been using the same corpus size, and that's been a challenge just because we wanted to cover many languages. And there is only that many data sets that will be comparable between many languages. So we use the Bible, sort of the good old Bible, in terms of having the same corpus translated in many different languages, and also Wikipedia. And yes, we restrict it to the same size because that can affect stability. And that's what we observed before when we focus on just one language, that depending on the amount of data that you have for training, you would have different stability. So yeah, that's a very good point.
All right. So there's a question in YouTube, but you already addressed this about should we accept that models achieving less scores on evaluation metrics? It's okay given that it's more efficient computationally, but I think you touched on this at the end of your talk. I'm not sure if you want to say more. But the trade-off between, let's settle for less accuracy because it's more efficient.
I definitely think we should do that. The challenge that I see, and I say it also as a, I don't know, maybe more senior researcher, that maybe it's, well, I think I have less to lose if I don't have a paper accepted. So I've been pushing more for papers that maybe lose in accuracy, but have these other aspects being addressed. I think it's something that we'll have to think carefully as a community on how we evaluate and how we don't push so much for just one factor, which currently is this, like, are you beating state of the art in certain numbers of how well the system does, ignoring all the other aspects? I think starting to make that more clear, like what are the trade-offs, actually reporting computational cost, environmental impact, all the other factors, like having some kind of maybe of a checklist where you report everything, and then you can see clearly where accuracy is versus the other factors. I really think we should do more of that. And one can call it a trade-off, and I guess it is a trade-off, but I think it's a trade-off that we have to make, because otherwise I also think, which I mentioned in passing, that we are in the danger of falling under a monopoly where only those who can afford big compute will
We
actually
sort of
get
are almost, I feel like we are already there.
We are already there, and that's because we only look sort of, we are, I would say, and again, we as a community, we're a little bit blind. We only look at this one facet. We see it, we only see that, and only that matters, without seeing that the other facets are a bit of a mess currently. So I think it will be very important to figure out, we are sort of under that tyranny of evaluation. Like we want to evaluate whatever we do, which I think it's good, but we'll have to think on how to evaluate, keeping in mind all the aspects.
Yeah, definitely. Well, I think we're going to have to close the Q&A because we have another session coming in, and we want to give like at least 5 minutes for people to stretch their legs. Thank you so much, Professor Rara Mihalcea, for being here. It was a wonderful, enlightening talk. I hope everyone enjoyed as much as I did. And with that, let's just take a 5-minute break. When we come back, Dr. Iram Calvo will take you from here to moderate the next session. What I'm going to do is I'm going to collect the questions and I can send them to you, Rada, and if you don't mind, and if you have some time, you can answer them in the YouTube, because the YouTube will be kind of like the permanent archive for this, and then some of the participants can see some other questions answered if you have time for those that we didn't get a chance to get to.
Sure. And thank you again for organizing this, and to all the participants. I look forward to seeing all the exciting research that you will be doing. And changing the face of the field, like really solving that Rubik cube.
There you go. Thanks, everyone.
Goodbye. Hello, everybody. Good morning, and welcome again to the Mexican NLP Summer School. So now we will proceed to our next talk. So let me introduce Dr. Sebastian Rudder to you. He is already with us, so I'm very happy to say hello to you. Thank you for being here. And well, it's a bit sad that you couldn't join us at Mexico, but well, here we are virtually as in most of the recent events we have. Okay, so Dr. Sebastian Rudder is a research scientist in the language team at Bitmine, London. He completed his PhD in natural language processing and deep learning at the Insight Research Center for Data Analytics, while working as a research scientist at Dublin-based text analytics startup Alien. Previously, he studied computational linguistics at the University of Heidelberg, Germany, and the Trinity College, Dublin. He is interested in transfer learning for NLP and making ML, machine learning, and natural language processing more accessible. So, well, the screen is all yours. Thank you again very much for being here.
Great. Thanks so much for having me here, and thanks a lot for the invitation and for organizing this event. Just to double check, can you see my slides? Is that, yeah.
Yes, we can see your slides, right?
Okay, great. Awesome. So yeah, so I think you've heard previously in the previous session from Rada already a bit about learning word embeddings across different languages. And in a similar vein, I'll be talking to you today about challenges generally with regard to multilingual learning in current NLP. And with that in mind, there are three things I would like you to take away from this talk. The first thing is simply the importance of not only working in English, but doing NLP for more of the world's languages. The second thing is just a general understanding of what the state of the art in this area looks like. So what are the models that achieve the best performance on data sets across different languages? And finally, and that's what I'm going to be spending most of the talk about, is to discuss some of the key modeling challenges I see in this area and potential solutions to address them. Now let's start with the first part of the talk. The main issue at the heart of my presentation is the issue of language diversity in NLP. And by that, I mean the discrepancy between the huge number of languages spoken around the world and the comparatively small number of languages that are studied in contemporary NLP research, which predominantly focuses on English and a small set of other languages that have large amounts of data available, both labeled and unlabeled on the web. And I assume, given that most of you speak not English as a native language, that I think this is an audience that is already pretty aware of potential downfalls and problems with this discrepancy. But to call out here the two big problems that I see with that is that the first one being that by focusing only on doing research on predominantly high resource languages, as a community, we're systematically excluding the more than 3 billion speakers of lesser resource languages around the world, because simply our methods are not able to serve or to support speakers in those languages. And to just cherry pick one out of a plethora of possible examples how this can affect the day-to-day life of these speakers. You can imagine in a post-COVID era where we can go out and go to eat in a city like New York, and you might use a popular maps application to enter a query looking for restaurants. And if you make this query in a language with a lot of data online, such as English, you will be presented with a number of different options. Now, if you make a similar query in another language with a lot of data, like Spanish, you're provided with a similar set of options as well. However, if you make the identical query in a language with much fewer data, like Basque, you're provided with no options at all. And given that this is an issue for what is still a European language, Basque, and data that is very commonplace, like data about restaurants, you can imagine how much more critical this issue is for most of the world's other languages, and with data that is much more important, like data about healthcare or clinical data. And the second important aspect here is that by focusing only on English and by designing using English for validating and testing our methods, we are to some extent overfitting on the linguistic properties and the kind of high resource settings that work well for English. As a result, our methods might not generalize that well to other languages with different properties. So while we've seen tremendous amount of success recently on common benchmarks like the Stanford question answering dataset, most of these successes have really only been achieved in languages with large amounts of data. Now with that, let's talk a bit about what methods that try to address this problem, that try to transfer or learn representations in many languages at the time look like these days. So just to recap, here the kind of core standard state-of-the-art method in NLP that you might have already heard about before is BERT. So a model that consists of multiple stacks of transformer layers. The model kind of looking kind of from the input here takes as input a sequence of subwords in language here English, which are generated using a separate tokenization algorithm. These subwords, for each subword, the model then computes a token embedding, a position embedding, and a segment embedding, which are fed into a stack of multiple transformer layers, which I'm not going to go into depth here at the moment. And then finally, the model is typically pre-trained using what is known as masked language modeling, where a random fraction of words in input are replaced with a mask token. And the corresponding masked words are then trained to predict at the output. And generally, this recipe of pre-training this flexible architecture on large amounts of data has been shown to be able to learn general purpose representations of language that can be applied and are useful for many downstream tasks. So the way methods like BERT are typically applied in practice are by fine-tuning all of the parameters of the model on data of a target task of interest, like the natural language inference task here, where we try to predict a relationship between a premise and a hypothesis sentence into one of entailment, contradiction, or neutral. And this general recipe, BERT, and subsequent variants of it have resulted in state-of-the-art performance across many tasks in natural language processing. Now in the multilingual setting, where we are not dealing with modeling just one language, but multiple languages at the same time, there are many of this current state-of-the-art models can be seen as multilingual counterparts to models that have performed well in English. So on that note, one of the most standard baselines in this setting is a model that is known as multilingual BERT. And multilingual BERT can basically be seen as a BERT model that is trained on data in many different languages, with a few other considerations. And the main kind of difference, or the main initial consideration here is now that because we feed not only one, but multiple languages into our model, the vocabulary that the model is provided now also does not only consist of subwords in one language, but subwords in many languages. The second step, the pre-training phase, is kind of conceptually the same as you would do it monolingually. Again, the model is trained using masked language modeling on batches in a given language. But now, again, during pre-training, the model sees not only data in one language, but many languages at the same time. And somewhat surprisingly, when these models were first proposed, people were initially quite surprised that even though these models are only trained and only ever see unlabeled data in different languages. So there's nothing in the pre-training task itself or in the pre-trained data that teaches the model what are translations or what are the alignments between words in different languages. The models still are able to learn robust representations across different languages that are transferable and useful for different downstream tasks. So because of the generality of these representations, these methods can also be used for cross-lingual transfer. So one way that these are commonly evaluated is by fine-tuning them on a given task. Again, here, natural language inference on data of a high-resource language like English. And then, because these models have learned robust multilingual representations, after having learned one task, the models can then be applied to the same task in another language and expect to perform reasonably well in most cases. Given that they've seen the target language data also doing pre-training most commonly. Now this is the standard recipe, so multilingual pre-training coupled with fine-tuning on a high-resource language, and then zero-shot transfer to a target language. And most state-of-the-art models in this area are essentially variants of this three-step recipe. So all of these models are still pre-trained transformer models, like Multilingual BERT. More recent models are called XLMR or ERNIE-M. These models also consist of increasingly large amounts of vocabularies, so about 250,000 tokens in multiple languages compared to the 30,000 vocabulary of English BERT. Also, these models consist of increasingly large number of parameters. So the current state-of-the-art models have around 500 million parameters in total. Current models are pre-trained on around 100 different languages, both on data from Wikipedia and from data on the web. To give you a general impression of how the recent progress in the development of these methods has looked like, you can see here the evaluation, the progress on the evaluation score for different models on a common benchmark in this area, which is called Extreme, which can be seen as a multilingual counterpart to the GLUE benchmark for measuring progress on monolingual transfer learning, which you might be aware of. And in this case, Extreme essentially evaluates these models on 9 different tasks in 40 different languages and takes the average of the performance across these tasks. And to just look at the most important value here, we can see here the progress on the average score on Extreme compared to the human baseline performance, basically an upper bound. And we can see here that even though there's been large amounts of progress initially from multilingual BERT to more recent methods, overall on the most recent methods, progress has somewhat plateaued. So we still seem to be quite a bit of ways away from bridging the last difference in performance compared to human level performance across these different languages. So in the rest of the talk, I want to talk about 2 modeling decisions and 2 problems in this area that I think could help address and bring us closer to human level performance when transferring across different languages. And the 2 modeling challenges I'm going to be talking about here regard 2 different parts of the transformer architecture. The first challenge regards to dealing with the overall model capacity, essentially how we can effectively use the capacity to do well in languages, in all kinds of different languages, in particular languages where we don't have a lot of data available. And the second challenge deals with how we process and how we encode our input data, because the tokenization method that we use to compute these subword tokens, while it is appropriate or can be useful for English, which is very morphologically poor, it's a far less optimal choice for many of the other languages of the world. So now let's talk about the first modeling challenge here. And the key issue that has been related to the problem of model capacity in multilingual learning has been known as the curse of multilinguality. And what that refers to is simply a trade-off between the performance on the model on any given downstream task and the number of languages that the model covers. Specifically to illustrate this, you can see here the performance on this natural language inference task that I mentioned in the beginning. As we train our multilingual model on an increasingly large number of languages, given that we keep the overall parameters of our model fixed. And as you can kind of imagine here, and what is somewhat intuitive, is that as we train our model on more languages, the overall performance of the model across these different languages decreases overall. And that is both on low resource languages as well as on high resource languages. And initially, and kind of an interesting phenomenon here is that as we increase the number of languages from 7 to 15 in our pre-training data, we see a small bump in performance here on the low resource languages, which can be attributed to better transfer from some of these low resource languages, so between the low resource languages and the high resource languages in our data. But then as we increase the number of languages further, even the benefits of this transfer diminish, and we get generally reduced performance. And this general phenomenon is kind of expected because you can imagine the more things you try to model with your methods, so the more tasks or languages or domains you try to model with a single model, the less parameters and the less capacity you have available for each particular setting. And that's a key issue at play here. So one way to address that is to simply scale up the parameters and scale up the capacity of the method. But in the end, ultimately, we don't really want to have to train or to use a trillion parameter model to do well on each of these individual languages, because for many of the settings we actually care about, having such huge models for use would be too cumbersome. And the current state-of-the-art methods that I mentioned before, just to reiterate here, basically is try to strike a balance between task performance, usability, and usability of the model by modeling about 100 languages during training. But the key challenge now here is, given that we have these kind of strong baseline multilingual models that capture 100 different languages, how can we still improve the performance of these models for the languages that we actually care about, whether they have been seen in the pre-trained data, but might not have enough capacity, enough data associated with them, or whether they have not been encountered at all in these 100 pre-trained languages. And the main kind of methodology that I want to share here is known as adapters for dealing with this setting. And adapters specifically go back to computer vision, where they've been first proposed in dealing and adapting to different tasks and domains for vision models. And these adapters you can basically view as small bottleneck layers that are inserted between an existing model's weights. So to make that a bit clearer, if we see here the standard transformer encoder layer that I previously only demonstrated schematically, each layer in transformer consists of a multi-head attention block, a feed-forward layer coupled with residual connections and layer normalization layers. Now, these adapter parameters can be inserted in different parts of the model, but a prominent and a well-performing location is to just insert them after the feed-forward block. And in this case, the adapter, the architecture of the adapter layer is very simple. It simply consists of a feed-forward down projection, a feed-forward up projection, and a residual connection. And in practice, these adapter layers are basically viewed as separate or independent from the remaining parameters of the model. And the main benefit of using these parameters comes from the fact that we can freeze the pre-trained parameters of our model and only learn the adapter parameters for a given task or a new setting. So we can keep all the remaining parameters of our model fixed and only learn this small number of additional parameters, which makes adapters a very parameter efficient and generally efficient way to deal with new settings. And the work I'm discussing now here is joint work with researchers from University of Darmstadt and Cambridge. So when using adapters in practice in this multilingual setting, you can view them as essentially learning transformations that make the underlying model more suited for doing well on a particular task. So instead of now fine-tuning all of the parameters of the model to teach it about a certain task or about a certain distribution, we can keep all of the remaining parameters fixed and only fine-tune these small additional adaptive parameters, which basically learn these transformations that teach the underlying model to do better on this on whatever task we fine-tune them on. So in practice here, in order now to adapt our model and make it more useful for a target language that you're interested in, we can simply fine-tune these adapters using our original pre-training task on mass language modeling, now using data only in that given language. So for instance, if we want to make our overall multilingual model more suited for just doing well in English, we can use an adapter and fine-tune only that adapter on data in English. Using mass language modeling. And similarly, if we want to make our multilingual model more suited to doing well on a Quechua language, we can do the same for data in Quechua. And the nice thing now is, because we keep all the remaining parameters of the model fixed and only learn these adapter parameters, the adapters are effectively interchangeable. So we can insert our adapters into our model to make the model more suited for English, but we can equally replace these adapters with the Quechuan adapters to make the same model more suited to the Quechuan language directly. Now, one thing I didn't mention here, so if we look at the overall architecture of the model, we can see that it consists of an embedding layer, both at the input and the output, coupled with these transformer layers, which consist of self-attention and feed-forward blocks. If we insert these adapters at every layer, we have additionally kind of a separate adapter layer at every layer block of our model. But one thing which we haven't adapted here in this case, and which hasn't been considered for adaptation in previous work, is the embedding layer. Because intuitively, if we freeze all the parameters of a model, the multilingual embeddings or the subwords in our model will still be more suited, or will not have been really adapted to the subwords we actually care about for our target language. So in addition, we also would like to add adapters or adapt our embeddings to some extent. And one additional thing that we can leverage here is the fact that in these state-of-the-art mass language models, input and output embeddings are typically tight. And this is usually just as a design choice in order to save parameters typically. So in order to leverage this fact now, adapters, so that we can both use the same adapters for the input layer and for the transpose of the embeddings at the output, the main kind of consideration here is to make them invertible. Because by encouraging or making these adapters invertible, we can effectively use the same adapter layer, so the same feed-forward up and the same feed-forward down protection, both to adapt our input embeddings, as well as to adapt our output embeddings to the target language. And for that, there's been different approaches proposed that we basically rely just here on previous formulation, which can be used to make arbitrary neural network layers invertible. Now, just to put different things together, you can basically use these adapters for multilingual transfer in a framework that we call MEDX, which consists of 3 different components. The first step, as I mentioned already before, simply consists of training these language adapters for your source and target language of interest. So both for English as well as for Quechua on data that is available for those languages like Wikipedia. In the second step now, because so far all of the adaptation that I talked about was just with regard to our language. But in practice, in order to make these adapters actually useful, we also want to adapt our model to our underlying task. However, if we would now fine-tune our model to the task, we would basically lose the information that we've already encoded in them, and it would no longer work as reliably with the adapters that we've trained using our fixed pre-trained model parameters. So in addition, we can also train a task adapter that we simply stack as a transformation on top of our language adapter. And the task adapter is learned on the source language, but could also be learned in different languages if the data is available for the task. on data of the task with the task-specific loss function. And here, again, for learning the task adapter, all the other parameters of the model are fixed, and only these task-specific adapters are learned in order to make the underlying model more suited for the target task of interest. Now in the final step, after we have frozen all the parameters of a model and learned these language and these task adapters, we can simply perform zero-shot transfer by substituting the source language adapter with the target language adapter that we actually care about, without ever having seen task data in the target language. Under the assumption that the task adapter is somewhat language agnostic, so that the model has been able to disentangle somewhat the language information in the language adapter and the task information in the corresponding task adapter. Now for evaluation, I just want to briefly highlight here just one setting where you could possibly apply this method to, and just to highlight essentially the settings where it outperforms standard fine-tuning of these multilingual models. And the main setting I want to highlight here is cross-lingual named entity recognition. In this case, you can see here the diagram on the left, which shows transfer from each source language to each target language on this task. So, for instance, we would train our model on English and then transfer to each language on the bottom there. And the languages here are shown kind of based on the amount of data that we have available. So where the languages to the top and to the left are more high-risk languages, and as we go to the right and to the bottom, languages become more low-resource or entirely unseen during pre-training. And what we can see here, based on the relative improvement that we show here compared to a strong state-of-the-art method that we use as the underlying model, we can see that the method particularly performs well when transferring from high-resource to low-resource languages. So effectively, the setting that is most common in practice is where this method is particularly helpful. However, at the same time, using these adapter layers in this modular framework, we can still achieve competitive performance also when transferring between high-resource languages as well. These adapters, the adapters that we trained, and adapters in general, are easily accessible and can be simply downloaded using this adapter hub that we made available. And in general, what I really like about this framework is that it's very parameter efficient. So if you want to transfer to different languages, or if you have different languages you actually care about, you only need to store one copy of your pre-trained model and only need to learn this small number of additional parameters for every task. And in addition, you only need to train these language adapters and the task adapters only once for each individual setting. So if you want to adapt your model to your language for many different tasks, you only need to train language adapters once and can then use them for many different tasks for transfer. So I think that kind of these aspects, in order to make it easier and kind of more practically useful to use these large multilingual models, I think make these framework quite effective in practice. Now, the second modeling challenge that I want to talk about here relates to the input representation, and specifically the fact that I mentioned before, that we use these subword segmentation for tokenizing our input in different languages. And one side effect of using the subword segmentation is, because the segmentation is done on frequency, so words that typically belong to high-resource languages, so languages with a lot of unlabeled data in the pre-training data, are associated with words that are only assigned either split in very few chunks or associated with single token, because they are seen many times during pre-training, like the word excitement here in English. And in contrast, now words in other languages that are seen less in the pre-trained data are split in correspondingly a larger number of chunks, such as translations of excitement in other languages here. And one particular consideration here is that because we ultimately expect for transfer for the model to be able to transfer the lexical information or the lexical knowledge it had from English to other languages or between the different languages, having these quite disparate tokenization patterns in different languages really hinders the lexical transfer of these models. So one way that we could try to counteract that is by using other forms of subword segmentation or subword regularization. And subword regularization on subword segmentation in general has previously been developed with a focus on machine translation. And one of the most commonly used methods for subword segmentation is known as byte encoding, but others have been proposed as well in the past. And these methods like byte encoding are generally known as deterministic segmentation methods because given an input, they assign and segment it in exactly one possible segmentation in terms of subword tokens. Now recently, there's also been methods proposed to do so-called probabilistic subword segmentation by, instead of using just one possible segmentation, training the method on multiple samples of possible segmentations, either by, in the case of byte encoding, simply dropping out possible merge operations in order to expose the model to different segmentations, or if you have a unigram language model that you use for subword segmentation, sampling different segmentations with the model. But the subword regularization, while this might be appealing for multilingual models, has so far only been used during training for machine translation models and only been shown to be effective there. So our the main goal of this project here was to try to use subword regularization also with multilingual models in order to make them more robust to segmentation errors during fine-tuning of these models. And one key consideration here is that if we just use subword regularization naively, we effectively have a mismatch between our pre-training, where we only see the deterministic segmentation, and our fine-tuning, where we would see the probabilistically segmented multiple segmentations of each input, as well as the test data, where we typically just want to use our deterministic segmentation for computational efficiency as well. So in order to mitigate this problem, we propose to train on both deterministic and probabilistic segmentations at the same time. So here, given an input X, we can compute first its BPE segmentation, so the deterministic segmentation and the corresponding loss, as in the cross entropy over this deterministic input. And similarly, we can compute the cross entropy over our probabilistic input as well. Combining those, we have a joint cross-entropy loss over both losses. In addition, another point that we found very useful here is to take inspiration insights from some work in semi-supervised learning, which tries to enforce consistency between model predictions under different input permutations. So in this case, as an additional auxiliary objective, we can enforce a consistency loss, which is simply here the KL divergence between our cross-entropy over the deterministic and the cross-entropy over the probabilistic input, in order to make the model more robust to produce similar predictions both over probabilistic and deterministic inputs. So that at test time, even if the segmentation of our input is erroneous, the model would still be robust and able to deal with that. And we can combine both of those objectives into a single loss at the end. Now the experiments, just to mention those briefly, are on different tasks of the benchmark that I mentioned in the beginning. With the general setting, again, is the sort of zero-shot transfer that I mentioned, where we train on English and then evaluate on data in other languages. And the models that we studied here are Multilingual BERT and another model XMR that we also used previously for comparison. And the main results what we show here in terms of relative improvement over both Multilingual BERT and XMR across the different tasks. So we can both see that for naively applying subword regularization, it helps on most tasks, but on some less than others. But in addition, using our multi-view subword regularization, where we in addition use this prediction consistency loss, leads to improvement on all of the tasks and improves and outperforms subword regularization across all the different settings. Now, just to share one final observation of the success of this method is that, interestingly, it performs particularly well on languages that don't have a Latin script. So we can see here again the relative improvement over the baseline model for these different tasks for languages with a Latin alphabet in orange and languages with a non-Latin alphabet in blue, both with our method and the subword regularization method, where our method has the darker bluer color. And we can see here that generally we get larger improvement for the languages in blue, so for the languages that have a non-Latin script. Because for those languages, arguably, the segmentation of the model would be less accurate because most or predominantly most of the languages seen during pre-training for these methods are typically Indo-European and thus use the Latin alphabet. So enabling the model to deal better with these different segmentation errors and to make it more robust to dealing with different possible segmentations makes it particularly robust for languages where it hasn't seen the corresponding alphabet or the corresponding script much during pre-training. So with that, I just want to conclude here and just summarize again the different, the main important takeaways from the talk, in particular, the importance of working not just in English, but on many different languages in order to broaden and enable NLP access for more people around the world. Secondly, the state of the art in this area, which mainly consists of these large-scale multilingually pre-trained transform models. And even though we've seen consistent progress on benchmarks like Extreme, there's still quite a bit of potential and room for improvement, particularly on languages with low resource data or languages with different scripts. And finally, I've highlighted two different modeling challenges. The first one being dealing with the capacity issue when transferring between different languages. And secondly, dealing with the issue of tokenization and segmentation errors in different languages. And I've proposed one solution in the form of adapters for the first setting, as well as subword regularization for the second setting. But even though those are kind of the main ones I've highlighted here now, I think there are many more interesting directions in this area and many additional ways to address these different phenomena, such as, for instance, instead of using subword representations, building on character level models directly. So with that, thanks for having me, and I'm happy to answer any questions.
Thank you very much for this interesting talk, Sebastian. Well, there are several things to note here. I think that last slide, which also you presented before, is very important because it shows the main takeaways from what you have been elaborating in this talk. So I would like to invite our attendees to pose a question. So please, if you have some questions, you can also ask through the YouTube channel. Please write your question and we will read it here. And also please use the question and answer button which is below in order to pose your questions. On the meanwhile, I would like to ask you, you presented different models that are useful for different applications such as Multilingual BERT and XLM. So do you think there is an idea on what to use previously beforehand? You know what it will be the dominion of application. How would you say if there is a method for recommending which model to use, or what are the characteristics that each one of these dominion have in order to have better or worse performance for each method?
Yeah, that's a great question. So in general, so in most of these experiments that I've mentioned here, we've And the most standard baselines in this setting are still these days like Multilingual BERT and XMR that I mentioned. Multilingual BERT has a smaller number of parameters. So if you're in a very kind of resource-constrained setting or don't have a lot of compute, that's kind of a good method to start with. And it's also a good method just to see and generally prototype if you're not yet sure if these models are actually useful for your setting. So it's something that you can easily test and run on your application relatively efficiently. Yeah, XLMR, particularly the larger version in contrast, has a lot more parameters. So it generally needs larger GPUs and smaller batch sizes, depending on your compute requirements. So that's generally more effective if you really want to get the best performance. And in addition to that, one thing that I didn't talk about here or didn't stress is the kind of the use case or difference between using monolingual models for your language versus using these multilingual models. And generally, I mean, in addition to this trend of training these large-scale multilingual models, there's been also the trend of training monolingual models, monolingual BERT models for different languages as well. And there are a couple of different studies in terms of looking at the kind of the benefits or the different use cases of these different models. So often, if you have sufficient label data or some amount of label data in your task and enough in your language, enough unlabeled data available for your language, and if there's already a off-the-shelf monolingual model, then it might be good to use also that as a baseline. However, if most of your data is maybe in a related language, then using these multilingual models and doing some cross-lingual transfer between related languages typically performs better.
Okay, thank you very much. We have another question from Dr. Nur Sabri Mitwali, and he asks, how can we apply the BERT model in Arabic language in this multilingual setting?
So in the multilingual setting, so Arabic is one of the languages these large-scale multilingual models have been pre-trained on, because compared to other languages, it still has a lot of data available online. So you could basically use these out of the box and just fine-tune them on data in Arabic if you want to apply them to tasks that you're interested in. At the same time, there's also Arabic monolingual models that you could use as well as another baseline for Arabic. So that's kind of the standard way that you could use them, basically.
Thank you very much. And what about the size of this training? We have already very big training size for GPT-3, for example. And then imagine if we try to do something similar, but multilingual, would need to grow so much to be very difficult to handle, or that it would require a very high amount of resources?
Yes, yeah. So that's kind of a big problem if you want to apply these methods to new language, or if you want to pre-train these models on new languages which were not covered yet. Then in order to expand them, we would need to allocate or make them much more bigger compared to monolingual models. In general, I think you probably because there's still, I think, some amount of positive transfer between different languages. I don't think that a model that is trained on 100 languages needs to be 100 times as big as its corresponding monolingual model. So I don't think there's the same factor that you need to apply here. But it definitely needs to be bigger to some extent, and also the vocabularies need to be larger. So in most of these settings, I would generally basically recommend, instead of trying to pre-train a huge multilingual model yourself, basically to use an existing model and simply adapt that for your new language if you think it's still underperforming.
Of course, yeah. Thank you. And we have a question from Saul Villatoro. He's asking about a variant of language. For example, Spanish from Spain, Spanish from Mexico, or even within Mexico, there are variations from the north to the south part of the country. So how the methods and technologies you are proposing can deal with these kinds of phenomena?
Yeah, that's a great question. And generally, these models rely, so Multilingual BERT was pre-trained on data from Wikipedia, and models like XMR are trained from data on the web. And in both of these cases, particularly on the web data, they rely on kind of off-the-shelf language identification systems, which I think, depending on the system, typically depending on the system, I think has separate tags or separate labels for different varieties of like at least Spanish, I would say. But for most of these other languages, different varieties are generally not detected. So they are simply treated as kind of part of the larger dominant language if they're covered at all. So it's generally, I think, really an important area for improvement to make these models more useful for different language varieties as well. But yeah, in practice, I think identifying the data is kind of the main issue, and then I think, given unlabeled data in those varieties, you could potentially adapt, fine-tune the model on data to make to teach the model something about the underlying variety. But I think there's still like an important and mostly open area of research, how we can most effectively use and really make these models useful for the many different language varieties around the world.
Yeah, that'd be very interesting to try. Thank you. There is another question from Professor Manuel Montes. Do you think adapters could be good for multimodal tasks?
Yes, definitely. So as I mentioned, they've been used previously for vision applications as well. So they are not restricted to any particular modality. And as far as I'm aware, they've also been used in some multimodal retrieval tasks, although I'm not exactly sure about that study. So I think this general concept of having like a modular framework or decoupling this information, I think is applicable in different settings like that, definitely.
I see. And in a similar line, we have another question from Professor Rada Mihalcha, and he says, "Thank you, Sebastian, for the wonderful talk." And she has been thinking about transfer learning from a major language to create resources for minority languages. What are your thoughts on going the other direction, from minority languages to major languages, to leverage some of the linguistic knowledge specific to certain languages, for example, word gender, levels of formality, politeness, etc., which may lexicalize differently in different languages?
Yeah, I think that's a great question. I think particularly with regards to dealing with bias or possibly toxicity or different connotations of taboo words in different languages. I think actually relying on multilingual signal can be quite important in terms of getting additional supervision or getting additional information for making some of those bias detection decisions. I haven't seen that many, or I'm not aware. I would love to see studies or pointers to any studies that effectively do this in that setting and show improvements. But I think that's a really great direction of research.
I see. Thank you very much. We have another question from Juan Flores. He asks, with those multilingual models, can we think of a GPT-like model in each language using one universal GPT-3 model? Is that possible?
Yes, I think that's completely possible. So most of the models I've talked about here and are basically these like encoder-only BERT-like masked language models. But there's also been a recent trend of training more GPT-3-like models. So whether these are directly autoregressive models or encoder-decoder models like T5. So there's a multilingual T5, for instance, that basically can also be used for multilingual generation. And going forward, I think I would personally like to see that we, as a community, or particularly these big institutions, will move away from just training ever larger models that only do well on English, and training models that can really serve many more languages at the same time. And I think we've already seen some indications of that in GPT-3 itself, which has already been shown, even though the authors didn't really put too much emphasis or too much consideration into the choice of languages in the pre-trained data. Despite this, because the model has still seen small amounts of different language data during its pre-training, was still able to do translation into different languages fairly reasonably. And I think if we just put more consideration into how we design our data and which languages and what types of data we sample for pre-training these large models, we can really reap benefits and actually make them directly useful for many more languages.
I see. Oh, there's a lot of things yet to explore in this direction. And Iman Jundi asks, when using a different adapter for each language and task, aren't we also losing some of the generalization gained from similar languages and tasks?
Yeah, that's a great point. So yes, basically by learning these adapters separately, we basically can't share information that we get during this adaptation phase. So we would hope that, or one assumption would be that hopefully most of the benefits from this positive transfer are already encoded in this multilingual model directly. But you're totally right that by learning these adapters separately, there's something that can get lost potentially. And one kind of recent direction that I've seen in order to address that could potentially be to try to either learn these adapters jointly for different languages, or you could kind of learn another meta model or like a hyper network basically that is trained to generate adapters in different languages, and that can then itself share information still between these the different languages these adapters have been trained on. So there's some that introduce additional complexity as well, but there's potential ways to counteract this issue.
Okay. Thank you. Leo Jackman says, related to the previous question, can you use an adapter to adapt a multilingual model to several languages instead of just one?
Yes, I think, yeah, you could definitely do that. I think here in this case, again, this kind of issue of model capacity comes into effect similarly to these large multilingual models. But because the adapters are a lot smaller and have a lot fewer parameters, it's a bit more crucial here. So if you want to use a single adapter for multiple languages, you probably want to use it for languages that are linguistically similar, or maybe varieties of the same language, so that the model does not have to model like two very distinct phenomena or different typologically diverse features in order to still get good performance for both.
I see. Thank you. Cristian Maldonado Cifuentes asks, looking towards the future, do you see a plausible path for the inclusion of very low resource languages, a path towards generalization?
Yeah, I think so another great question. I think generally I think people in NLP disagree with generally a bit of this terminology in terms of what is actually a low resource language. I've kind of used the term a bit in a hand-wavy fashion by just referring to low resource languages that have very few amounts of data online. Yeah, and I think we can kind of make a more fine-grained differentiation that, for instance, if we look at Wikipedia, we have around 300 languages there which have some amount of data, but many of those languages have very small Wikipedia articles. And even though on the web we have generally more data because our current language ID systems typically cannot cover that many languages, it's also the problem of simply finding additional data for those languages. So I think, I think overall we've seen that these models, in order to that the current types of models, neural networks that we're using, we can do very well if we have sufficient data for different languages. So I think one key important step to enable more access for these languages is simply to make it easier to get data, whether that is in broadening the coverage of language ID systems, gathering more unlabeled data, analyzing the data that we already have. Previous studies have found problems in terms of the quality of resources that were claimed to cover around 100 different languages. So both looking at that. And then I think additionally also simply creating new data resources I think is tremendously important and useful for such low resource languages, because having labeled data available really incentivizes people to actually, or really enables us to evaluate on them in the first place. And finally, maybe also with regard to the point that Radha mentioned towards the end of her question answering session, looking at additional existing or new resources or different sources of data. Because for many low resource languages, while text data might not be that easily accessible, speech might be a lot more common or easier to obtain at a larger scale for those languages. So I also hope, and I particularly see here in this case for doing NLP on low resource languages, the promise of multimodal or a more speech-centered NLP.
Thank you. Roberto Lopez asks, great talk, thank you. What is a more effective approach, fine-tuning or transfer learning?
So I guess, yeah, these days transfer learning is used to refer to a lot of different adaptation methods, or using some information, some knowledge from one setting to another. And fine-tuning here, the way I've used that is essentially as the current standard form of transfer learning, basically, where this like transfer learning recipe is basically consisting of pre-training general purpose representations and then fine-tuning and then transferring them via fine-tuning to new task. As I mentioned, with these adapters, fine-tuning can be a bit problematic, particularly if you have a very large model that you want to update. So there are kind of a number of recently proposed more parameter-efficient strategies where adapters is just one of them. One alternative promising method, for instance, is prompt-based adaptation, which we've seen in GPT-3, where instead of adapting the entire model, you can just simply use a prompt to teach the model something about the downstream task. But also with these prompts, these typically need to be carefully engineered, and you need to have very large models for them to work well. So in general, I think still fine-tuning or doing some version of parameter-efficient fine-tuning is still kind of the main way to go, possibly with with using prompts as well, but combined with still updating some amount of the model parameters.
I see. And we have a last question with it's kind of comment. Emmanuel Rosillo says, I think it would be better to divide these adapters as subtasks and bundle them to a main adapter that divides it according to the requirement. What do you think about this?
Yeah, that's a great idea. I think generally, I mean, these adapters are kind of related to generally maybe more theoretically oriented work in terms of disentangling information in these models. Here, starting from pre-trained models. So if you have some idea or some objective in mind in which the model can kind of itself discover possible sub-layers or additional blocks in which it can allocate itself the information, and then maybe identify more interesting or more useful pairings. I think that kind of direction is very interesting too. Okay, thank you very much. I think this is these are all questions. Thank you very much for answering all of them in detail. Thank you also for your talk. I think, as you could see, there is a lot of interest in this, and well, there is a lot more to explore. Thank you very much, Sebastian. Thanks for having me, and thanks for the great questions.
Thank you, everyone. And well, for all our attendees, please go to the session that corresponds to the tutorial you were interested in. So, well, again, thank you and see you soon. Goodbye.